Hello, everyone. Welcome to today's AGT seminar. Today, Antonina Khramova from Eindhoven University of Technology will tell us about algebraic bounds for some rank metric codes. Antonina, please.
Yes, thank you for the introduction. So yes, my title is Algebraic Bounds for some arithmetic codes. There's a code in the title, so this gives a clue that it will be coding related talk, coding theory related. So at the start, I assume that most people are familiar with the Hamming metric, which is a metric space defined on vectors over a finite field. In this example, it's just F2. And we define a Hamming distance between these vectors by taking the sums of the sum of differences between the respective entries of the vector. So I am going to talk about some arithmetic codes, and some arithmetic is a extension of this idea of the Hamming metric. So here, instead of vectors with entries over finite field, the entries are actually matrices also over a finite field, in this case also F2. The matrices can be of different sizes, like here, not necessarily square matrices also. And the distance between two tuples of matrices is the sum of ranks of the respective entries of the tuples. So this one's here, this one's from there, and etc. Yeah, so the sum rank distance between the two tuples is the sum of ranks, which gives it the name sum rank. So here is the more formal definition. We denote the sum rank metric space with this product. N_i's and M_i's are the sizes of the matrices. Q is the size of a finite field. Yeah, and the sum rank metric distance is the sum of ranks between two matrices. Yeah, so if you're wondering why do we study sum rank metric at all when we have a Hamming metric, which is much more familiar to everyone and more easily structured, there's a motivation that comes from network coding. So in network coding, we have a network of nodes with a source and terminals. And the goal here is to transmit messages, which are here vectors over a finite field Q, of size Q. And what we want to do is we want to transmit these messages to the terminal nodes in a way that every terminal gets all the messages that we want to transmit. So here we have two messages. We can send them over two different arcs of the network. Then whenever a node gets just one message, it's the easiest thing we can do is just to transfer this exact message further. Yeah, but when we have a node like this, which gets two messages, we need to decide what to do with it, because if we just choose to transfer exactly one message, this doesn't work, since this terminal doesn't get the V2, and that's not allowed. So instead, we need to find a way to combine the messages together. So in this case, it's just a sum of two vectors. And then we can define a rule in which, by which we combine the messages here, and then define a rule to decode the message that we receive in the terminal, so we get both messages like we need. So the problems here start when an error occurs. So if we have an error occurring in one of the edges, it transfers to all the following edges, and it can even propagate. We call this error propagation when we have a node which has many outgoing arcs. And so this is where the rank metric codes come in. So in rank metric, if we look at the rank distance instead of Hamming distance. There are theoretical results that help us not reduce, well, they help us bound how much propagation is allowed, so we can more clearly define what kind of code we need to make sure that we can deal with fixed number of defect arcs in the network. So this is motivation to study the rank metric codes, and some rank metric codes is a generalization of rank metric, of course. Yeah, so the problem that I'm going to focus on is not specific to network coding. It's actually a classical problem of coding theory. Here we have a code with minimum distance, d, which just means two elements of the code have to be a distance at least d from each other, meaning the sum rank metric distance here. Yeah, and what we're interested in is finding out what is the maximal size of a code that satisfies this condition about the minimum distance. There are several upper bounds on the size of the sum rank metric codes. So in this point, I have 8 bounds. They all come from the same paper from 2021, and they mostly come from adapting classical coding arguments to sum rank metrics. So you can see that there are some mentions of singleton, like sphere packing argument, Plotkin, Hamming. So all these classical results that are known for, let's say, Hamming metric or some other metrics transferred to the sum rank metric. I'm going to talk about 2 new upper bounds on the size of the sum rank metric code. The first bound is, we call it the ratio type bound. So it comes from a connection to the k independence number of a sum rank metric graph, and then we introduce a spectral bound from there. And the second bound I will define is the Delsarte bound. So it's a bound that comes from applying the Delsarte's LP approach to sum rank metric codes. The Delsarte bound has been done for many other metrics like Hamming metric and rank metric, but not for sum rank metric. So this is the gap we are filling. Yeah, so this is the outline of the talk. We are right now here at the end of the introduction. Next, I'm going to explain the ratio type bound and define the sum rank metric graph to introduce it. Then I'll explain the Delsarte's LP bound in general and hopefully address why it's hard to do it for sum rank metric, why it hasn't been done before. And then we'll actually we'll address it for sum rank metric and introduce the Delsarte LP bound. Yeah, so we first start with defining a graph. So we define the sum rank metric graph in a very standard way when it comes to defining graphs on a metric space. So the vertices of the graph are just the elements of the sum rank metric space, so the tuples of T matrices. And 2 vertices are said to be adjacent if the sum rank distance between them is exactly 1. So here is one of the smallest non-trivial examples of a sum rank metric graph. Here we just have T equal to 1. So there's one matrix in a tuple, and it's a matrix of size 2 by 2 over F2. So this is what it looks like. You can probably find, yeah, the 0 matrix here and check that it is only adjacent to all the 2 by 2 matrices of rank 1, which is what's supposed to happen. Yeah, in this case, when T is equal to 1, these graphs are also widely known as bilinear forms graphs. So it's just exactly the same definition, except we restrict T to 1. And if we want to take it one step further and have t equal to 2, so here we have now two matrices in the tuple. The first one is 2 by 2. The second one is just 1 by 1. So over of 2 is just 0 or 1. The graph looks like this. So it's actually related to the bilinear forms graph from before, and it's actually a Cartesian product of the original graph and K2, which is just bilinear forms graph for the 0 and 1, since it's just two vertices and they're adjacent. Yeah, so this is what the sum-arithmetic graph looks like. And what we need to define the bound is introduce the k-independence number. So k-independence number is a generalization of the usual traditional independence number. It is the minimum number of vertices in a set S, such that distance between any two vertices in S is more than k. So this is actually related to the size of the maximal size of a code with minimum distance. So actually alpha d minus 1 is exactly the size of the maximal size of a code with minimum distance d. Yeah, so our question from before on upper bounds on the size of the code becomes now a graph theoretical question. What is the upper bound on the alpha d minus 1, so on the d minus 1 dependence number? So to answer that, we can look into spectral bounds on the independence number. This is a classical result for the alpha 1, the usual independence number, the Hofmann bound, or also known as the ratio bound, which uses the eigenvalues of the graph to bound the independence number. Yeah, specifically the largest one and the smallest one. So this bound actually has a generalization to alpha d minus 1 for any choice of d. It looks maybe a bit confusing at first, but the main point is it also uses the largest eigenvalue and also in a way the smallest eigenvalue, but with respect to some polynomial p, which is just a polynomial with real coefficients of degree d minus 1. And wp is the largest element of the diagonal of p of a, which is a JCC matrix. Yeah, so the structure of this bound is actually very similar to the ratio bound for alpha 1. And that's why we call it the ratio type bound. And actually for d equal to 2, this coincides with the Hofmann bound with the proper choice of p. So yeah, the main challenge here is to figure out how we want to define p. So the theorem just states that we can choose any p and the bound will be correct. But of course, we want to minimize the right hand as much as possible. So you probably want to choose p in some good way. So yeah, for d equal to 3, this is actually done in the same paper by Abiad, Protein, and Fiol in 2019. And for d equal to 4, so for alpha 3, the result by Kavi and Newman. Yeah, so what they do is they derive the polynomial p, which optimizes the right-hand expression in this bound and provide the best polynomial for this bound. In general, for d larger than 3 or 4, we can also use the Fiol's LP. So this LP constructs so-called minor polynomial, which minimizes this expression, which is basically the right-hand expression of the ratio type bound. And in general, this method works only for d-1 walk regular graphs. But we also know that the sum rank metric graphs are all walk regular for any choice of d-1. So we can use this LP to compute the ratio type bound, but only if we know the eigenvalues of the sum rank metric graph. But this is also can be solved because we know that the sum is the Cartesian product of bilinear forms graphs. So we actually seen it before in the example. So when we started with a bilinear forms graph for the 2x2 matrices, and then we got the sum rank metric graph for 2x2 and 1x1 matrices by taking the Cartesian product of two graphs. So this idea actually works in general. So any sum rank metric graph can be represented as a Cartesian product of T bilinear forms graphs, where each graph kind of corresponds to each matrix. And the good thing about this structural result is that for bilinear forms graphs, we know what eigenvalues look like. So this is the formula, which only depends on the sizes of the matrices and the size of the field. Yeah, and of course, if the sum rank metric graph is a Cartesian product, we also have the eigenvalues of the sum rank metric graph by extension. So it's actually very easy to compute the eigenvalues of the sum rank metric graph, which means that we can use these eigenvalues to plug them into this LP and then compute the ratio type bound from there. So this on the first bound. The second bound is Delsarte LP bound. And yes, this is a classical bound in coding theory. It was introduced for many metrics, originally for Hamming codes, but then later also for rank metric codes. Both of them are partial special cases of the sum rank metric. But for the general case, the sum rank metric itself, it has not been done yet. So this is what we are doing here. Yeah, to introduce the Delsarte LP bound, I of course need the definition of a symmetric association scheme, which I hope that most people know, but I included it on the slide just to be nice. So the first two conditions are very simple. It's just that we have one relation that is reflexive. All relations in the scheme are symmetric. And this third condition is usually the most complicated one. But if you know what the distance regular graph is, then it should also look familiar. So it basically says that if we have a distance regular graph, then we can define an association scheme for it if we take the distance relations as the relations of the scheme. So we say that two vertices are in relation Ri if the distance between them in the graph is I. A well-known example of distance regular graphs are Hamming graphs. So for them, we can define a Hamming scheme. I have a small example here with a cube. So R0 is just relation of vertices being by themselves at distance 0. The R1 corresponds to the edges. R2 are just for vertices at distance 2. And there are 4 pairs of vertices at distance 3 in the cube. So here they are in the association scheme. Yeah, apart from Hamming graphs, bilinear forms graphs are also distance regular. So for them, we can also define a bilinear form scheme, just using the same logic as with Hamming graphs, but for bilinear forms. Yeah, and for any association scheme, we can consider the Bose-Mesner algebra that arises from this association scheme, and we can define the Q eigenmatrix or the second eigenmatrix. So here, I define it specifically for the bilinear form scheme. And bilinear form scheme are self-dual, so the second and the first eigenmatrix are actually the same. So for bilinear form scheme, we can actually define the exact entries of Q without going into the details of Bose-Mesner algebra. We just, as long as we have eigenvalues and the intersection numbers of the bilinear forms graphs, you can just use this recursive formula to define the entries of the matrices. And of course, the eigenvalues and the intersection numbers are also known for bilinear forms graph. And they only depend on the size of the field and the size of the matrix here. Yeah, so the reason I'm going into details for the second eigenmatrix is because I will need it to define the Delsarte bound. Another term that I need is the distribution vector. So for an association scheme and for a subset of the point set of the association scheme, the distribution vector is just a vector that in a way shows how the set delta is distributed over the relations of the scheme. So Delsarte in his thesis showed that for any choice of delta, this inequality holds, which connects the distribution vector and the second eigenmatrix of the scheme. And this inequality can be used as a constraint in the linear programming bound here. So what is happening here is we want to maximize the sum of entries of the distribution vector, which is exactly delta because of how it's normalized. The most interesting condition here is this last one, which says that I is equal to 0 if I is less than predefined D. But as we know from how bilinear form scheme is defined, the relations Ri with I less than D is just two vertices being a distance less than D from each other. So basically what we are doing here is we are saying that two vertices have to be a distance at least D from each other in the set delta, so which makes delta code with minimum distance D, which is exactly what we need because what we are doing is maximizing the size of this code. Yeah, so to recap, when we are dealing with distance regular graph or graph in particular, we can define this association scheme for any distance regular graph, and we can use this LP to compute a bound for the size of the code with given minimum distance. And everything works out fine for Hamming graphs and bilinear forms graphs. But now the question is about the sum-rank metric graphs. So are they distance regular? Can we do the same trick for them too? And it turns out that unfortunately, no, the sum-rank metric graph is not distance regular in general. So it is actually only distance regular in two cases, when we have t equal to 1, or when we have t more than 2 and all blocks have this form. So all matrices are just 1 by m, which is basically a Hamming case. So it is the same as saying that the graph is the Hamming graph, and this is the bilinear forms graph case. So yeah, the graph is only distance regular in these two cases, and these two cases were also covered by Delsarte himself. So it is not very interesting to apply the bound to those families because it has been done already. And we are interested in what is happening in between. So this is kind of the main challenge here is to how to do that when we don't have a distance regular graph. But in principle, we don't actually need a distance regular graph to apply the Delsarte bound, because the Delsarte bound only asks for an association scheme. And just because we can define it in an obvious way, as we can do it for distance regular graph, doesn't mean that we cannot define it at all. So this is what we do. We define an association scheme for summary metric graph in a different way. And for this, we need this operation of direct product of two association scheme. So here we start with two association schemes. And the point set of the product is the direct product of the 2 point sets of the schemes. And the relation is also kind of a direct product of the two sets of relations. And here we say that x1 and x2 and y1 and y2 are in relation Rij if the first two vertices were in relation I in their original first scheme, and the second two vertices were in relation J in their second scheme. So to illustrate this idea a little bit, I have this example here. So if you want to look at the example of a summary metric graph from before, and specifically at two vertices, 0 matrix 0 and identity matrix 1, we say that they are in relation R to 1 with each other, because the rank distance between the first two red matrices is 2, which can be seen by this graph. This is the shortest path between them. And the rank distance between the second matrices is 1, which is represented by this blue edge. So this is how we define the relation. So 2 for rank distance between the first matrices and 1 for rank distance between the other two matrices. Another example here is the Hamming cube from before. So it can also be seen as a Cartesian product of 3 K2s, and we can kind of construct a direct product of association scheme where each scheme is defined for K2. So we start with just K2. It's a very simple association scheme with zeros on the diagonal and ones off diagonal. And when we want to take a direct product of the red edge and the blue edge, we get something like this. So if you pay attention to the red indices, we have just 0, 0, 1, 1 matrix here and over there also. And if you look at the blue indices, you have 0 here, 1 here, 0 here, and 1 here. So in a way, it is kind of structured like a Kronecker product, but instead of multiplication, we get the like tensor product of it. Yeah, and if we want to take a direct product of this square and another edge, we get the Hamming cube, and we get this association scheme. It has 8 relations to the power of 3, which is just to remind you different from what is the Hamming scheme for this graph usually. So this Hamming scheme from before had 4 relations because there are 4 possibilities for distances between the vertices. Here we have 8. So yeah, it's a different scheme, but it's a good thing for us because we wanted a different scheme since this scheme did not generalize to the summary metric graphs. So yeah, to reiterate, what we did is we started with the summary metric graph. We know that a summary metric graph is a Cartesian product of T bilinear forms graphs. We know that each individual bilinear forms graph is distance regular. So for these T graphs, we can construct T bilinear form schemes. And now we have this direct product operation to combine them into one big scheme. And the question is, like what is the scheme can be connected back to the sum arithmetic graph from which we started. Is it a good scheme to run the Delsarte LP on? And a good scheme is a bit odd choice of word because it kind of implies that we can compare the schemes with each other in some way. And actually we can do it with the fusion. So we say that for two schemes that are on the same point set X, the first scheme is a fusion of the second scheme if the relations of the first scheme are just unions of relations of the second scheme. When we are talking about the off-diagonal ones, the diagonal one has to stay the same, of course, for it to be a scheme. Yeah, so here R1 prime is the union of these two. This one is the union of these two relations. So A1 is a fusion of A2. And another thing I'm defining is the Weisfeiler-Lemon closure, also known as coherent closure. In general, it is defined for coherent configurations, which are generalizations of association schemes. But for our purposes, we can define as an association scheme for a graph, where the point set is just the vertex set of the graph, and the relations are need to satisfy these two conditions. So there should be a union of some relations that is equal exactly to the adjacency relation, and it is also the smallest such association scheme in terms of fusion. So this coherent closure is a good scheme to run Delsarte LP on because because of the first condition, it respects the adjacency relation between the vertices, and also like all the distance relations. We don't have like two vertices that are distance less than d and two vertices that are distance more than d, all fused into the same relation because of that. But also it is the smallest scheme in terms of the number of relations, and the number of relations is the size of the Q, the second eigenmatrix, and that is essentially the size of our linear program. So the smaller it is, the better for us computationally. So yeah, this is what we call a good scheme. And the question is, how does this compare to the scheme that we introduced, the direct product of bilinear form scheme? So our main result of the paper is that it does compare. So the coherent closure is a fusion of the direct product of bilinear form scheme that we introduced, which means that the scheme that we give is not necessarily the smallest one in terms of fusion, but you can use it to run the Delsarte LP bound on it and still get the result. And that's what we did in our computational part of the paper. So here we have a table of several sum arithmetic graphs, and then them are the sizes of the matrices. D is for the minimum distance of the code that we're looking for. Yeah, T is the size of the tuple, and Q is the size of the field. These 6 columns are the coding bounds, so the ones that were introduced before using the code theoretical methods. And these 2 bounds are the ones that we introduced, the ratio type and the Delsarte LP bound. And you can see that in all of these examples, the Delsarte bound is the best one. So in these examples in the table, it strictly outperforms all the other ones. But we have not seen any examples where Delsarte LP is strictly outperformed by some other bound. So it's always either strictly the best one, or it is equal to one of the bounds that were known before. Yeah, so overall, it's a good choice of an association scheme, or a good choice of a bound, if it can beat all the other ones. Yeah, and for conclusion, I have some open questions here. So one natural open question for whenever we introduce a new bound in a code is constructing the codes that achieve this bound. So so similar to Reed-Solomon codes for singleton bound in Hamming metric. And this has not been addressed in SumRank metric, mostly because people don't really know how to construct optimal codes for Delsarte LP in general. So there is some progress for Hamming and rank metric, and maybe it can be transferred into the general case of SumRank, but it's not clear how to do it now. And the second question, of course, is can we use this Delsarte LP approach in other metrics where we have a similar problem? So when the respective graph is not distance regular by itself, but has a symmetric structure, can we use the same idea to introduce the Delsarte LP bound for those metrics too? And that is it for me. Thank you for your attention.
Thank you for the nice talk, Antonina. Any questions? When you mentioned the field, the good schema, the good fusion schema from the with Feller, Lemon, Cooler thing. So I forgot the name. What is it? The sum rank metric graph is the Cartesian product of some bilinear form graphs. Is the adjacency matrix with this Cartesian product in the good schema, or it has been merged with the other matrices?
Sorry, can you repeat that?
So you define the derived product schema. Then you find the good schema that satisfies the closure condition, which is good. I'm wondering whether the adjacency matrix is of the Cartesian product the adjacency matrix of the sum rank matrix graph is in the good schema.
Yeah, I mean the problem is that like if you're just looking at the distance matrix of the sum-rank metric graph, it does not like form a scheme by itself because it's not a distance regular graph in general. So that's why you have to like go around with the direct product of schemes.
Yeah. Like in the direct product of the schemes, there are many zero matrices. Then when you try to find a good scheme, some of them are summed up together to find to have a scheme of your matrices. I'm wondering in this new collection of matrices whether the GCC matrix or the graph is inside.
Yeah, I'm not sure about that.
Okay.
Yeah, there is a question. Is there any result of some rank metric defined on FQ for Q more than 2? So all the results here are for general Q. Including the coding bounds from before, from the paper from 2021, they are all for Q general. So may have confused everyone by taking the examples with just Q equal to 2, but it works here.
Yeah, I guess it's harder to tell if you have a bigger Q.
Yeah, these graphs get very big very fast.
Yeah.
Not always good for examples.